So we've already looked at some common bases, and we've dabbled a bit in substitution reactions. What I actually want to move into is, instead of talking in more detail about substitution reactions, which we talked about at length in Organic Chemistry 1, is I want to move right into elimination reactions. So these are going to be elimination reactions under basic conditions. Okay, the important thing to recall about elimination reactions is this term anti-periplanar, where elimination reactions usually occur with an anti-periplanar conformation. Now, there's a few ways that we could visualize this. We could go back into our Newman projections, but what I'll just kind of say is that if we allow the bond from which elimination is going to occur, if we let that bond be parallel to the horizontal axis of the paper, just the bottom of the paper, and we let the leaving, then we want to put the leaving group and the hydrogen to be removed by deprotonation. We want to put those in plane, but on opposite sides of the bond that's going to accept the double bond. Then we have some base, which I'll write as A minus, that comes over, attacks the hydrogen, pushes the electrons down to make a double bond, simultaneously pushes the leaving group off. This allows for the most productive overlap of orbitals to give rise to our alkene. So this is our product, the alkene. The other products we form are HA, and then the leaving group as a negatively charged species. So the groups must actually, it's not really an option. When we have a concerted elimination where everything sort of happens at once, the H and leaving group must be arranged anti-periplanar. Because you cannot sort of allow, the orbitals must be perfectly overlapped. Otherwise, you have to rely on a stepwise mechanism involving multiple intermediates, as opposed to this nice concerted elimination. So if we want to think about some experiments, let's say that we have some leaving group, OTS, next to some hydrogen, but that hydrogen's on a cyclohexane ring that also has a CH3. And then let's go ahead and block the other side, so we can only consider deprotonation at the position next door to the OTS, adjacent to the OTS. And what I want to ask is, what stereochemistry would be required for the basic base-mediated elimination to form this product, okay? What stereochemistry is allowed for, or is required, is required for elimination to occur. Okay, so let's kind of consider our options here. We could have the OTS as a wedge, and then the CH3 as a dash, a wedge, and then the hydrogen as a dash. Or we could consider something where the OTS is a wedge, and then the H is a wedge, and the CH3 is a dash, plus the enantiomers. For the moment, let's not consider the enantiomers for this particular molecule, and just think about what stereochemistry would allow for the elimination to occur. Well, what I want to do is I want to I want to draw the chair structure for both of these so that we can see what the arrangement for these groups would be. So you'll have to excuse me. Sorry about that. I had to tend to some kids stuff. Let me get my notes back in front of you. So I want to consider which of these stereochemistries would allow for anti-periplanar arrangement. To do that, I need to look into the chair structure. So let's draw the chair structure for each. Okay, so in this first chair, I'm going to put the OTS up because it is a wedge. And then over here would be the two methyl groups. And then here the CH3 is up and the H is down. So I'm going to let A minus sort of come in, which is my base, grab the H, push the electrons over, and then kick off the OTS. Versus an alternative version where the only thing that has changed is that the equatorial and axial groups at the leftmost point have flipped. This is a diastereomer of the original molecule. Now A minus would need to come here and grab the hydrogen this way and push the electrons off. So the curly arrows are the same in both cases, but what I want you to notice is that between each of these, we have an anti-periplanar arrangement of the OTS, the H, across the carbon-carbon bond that's going to accept the alkene. So this is a good situation, and this would go on to form the product. Now here we're not actually going to see this reaction occur because what we have to note here is that this is not anti-periplanar. And I grabbed too much, or I mean, excuse me, I grabbed the CH3. I meant to grab the H. You can see the H is kind of kinked off to the side, so this is not anti-periplanar. And so this would not form the product. So as a result, what we would have to do is we would have to say that the diastereomer shown on the right where the H is up would not actually give rise to product. You would see no reaction with the strong base because you don't have a hydrogen adjacent to the leaving group that's capable of eliminating to form the carbon-carbon double bond. Okay, so that is an example of an elimination reaction. Let's look at another example. This one's kind of a bit, I'm going to leave this here. I'm going to introduce kind of a bit of a sort of an awkward, I guess, I don't know, it's an unusual elimination reaction, and it's silyl elimination. Silyl, this implies a silicon atom, and it's usually in the form of TMS, which is trimethyl silyl. So what we can do is actually use an interesting property of silicon to promote some interesting chemistry. Namely, we can take advantage of the fact that when silicon is attached to fluorine, the bond dissociation energy is 130 kcals per mole. Now, in comparison, the CH bond BDE is 98 kcals per mole. Now, what a BDE is it's a bond dissociation energy. It's the energy required to dissociate the covalent bond into two free radicals. Okay, so the CH bond is sort of the gold standard. And so the fact is, because this energy is sort of the gold standard, about 100 kcals, we would consider anything above 100 kcals a strong bond. We would have to say then that the silyl fluoride is more than 25% stronger than a CH bond. We don't really do too much with CH bonds in terms of the chemistry that we know about. So what I'm trying to say is this is a very strong bond. Okay, now we're going to take advantage of that to do some interesting silochemistry. So for example, if we, reaction I've actually gained a lot of experience with, it's going to be easier. Let's be careful about my double bond. So I'm going to put a double bond, the rightmost carbon-carbon single bond. I'm going to have the double bond there as well. So pay attention to my double bonds in this case. It's not a big deal. It's just for visualizing what's going on. It's a little bit easier to see this resonance form. Okay, if you react this molecule with a salt called cesium fluoride or any other of a number of fluoride sources, cesium fluoride's quite good because this is a soluble salt. What you can do is you can kind of cross out the cesium and consider the fluorine anion. Now, TMS is the same as, I should have drawn it this way, Si with 3 methyl groups attached to it. So let me just redraw that down here. So we have OTF. Okay, now what happens here is the fluorine engages the silicon, okay, and actually coordinates to the silicon to form a pentacoordinate, that is 5 things added to the atom center species that's negatively charged. And it does so because we have this really strong bond. And that strong bond will, with its negative charge, actually dump the electrons down to make a carbon-carbon triple bond and push off triflate, which is, again, an incredible leaving group, to give rise to a ring system that we'll get to in a second. Fluoro-trimethylsilane, TFO minus, and then the ring system is actually a benzene with a triple bond. This is the molecule, not benzene, but rather benzyne. Benzyne is a useful molecule for generating molecular complexity on aromatic rings. It's highly electrophilic. Phrase I like to say is it reacts with anything on the shelf. That's definitely an overstatement, but it's fairly electrophilic and it has general reactivity and it doesn't have a lot of steric hindrance. You can do a lot of interesting things with benzyne, including pericyclic reactions and that sort of thing. Kobayashi, a scientist, was the one that discovered this fluoride-mediated silyl triflate elimination to give rise to the benzyne intermediate without using harsh reagents, I should say, that would otherwise destroy the benzyne intermediate. So pretty interesting chemistry. It really opened the door for studying this complex intermediate and things like it. So that'll do it for eliminations.